To my fellow reporters, classmates, and especially to our professor in this subject, Sir Danimar Naipa. A compelling day to all of you. By the way, my name is Mary Grace S. Enerlan, one of the reporters coming from Group 6. For today's topic, I will be discussing to you what are the factors influencing the wave velocity. But before we go further from our discussion, let us all first identify what is wave velocity. So wave velocity, it is given as the velocity associated with the disturbance propagating in the given medium. It is also distance traveled by period motion per unit time. So what do you think are those factors influencing wave velocity? Do you have any idea? Let us all find out. In this presentation, you will see the 5 factors influencing the wave velocity. First, we have the wave type. Second is elasticity, density, and temperature. Third is rock materials. Fourth is depth. And fifth is Poisson's ratio. In this video, I will be only discussing the 3 factors, which are the rock materials, depth, and Poisson's ratio, while the other 2 will be discussed by my partner. First, we have rock material. Some of the studies said that the types of rocks are one of the factors that influence wave velocities. There's an average compressional wave velocities at 600 megapascal and 300 degrees Celsius in a variety of crustal rocks. That was according to Candy 2016. Serpentinite, metagraywacke, andesite, and basalt has a limited velocities to 6 kilometers per second. While many rocks of diverse origin, which are the slate, granites, altered basalts, felsic granulite, has velocities between 6 to 6.5 kilometers per second. Most rocks like mafic and composition, which include amphibolites and mafic granulites without garnet, has velocities of 6.5 to 7.0 kilometers per second. Marble and anorthosite are the minor components in the crust based on exposed blocks of lower crust and xenoliths. Gabbro, garnet amphibolite, and mafic garnet granulites are the rocks with average velocities of 7.0 to 7.5 kilometers per second. A non-serpentinized ultramafic rocks and eclogite, a high-pressure mafic rocks, has a velocities above 7.5 kilometers per second. It is very important to know that the order of increasing velocity is not a simple function of increasing metamorphic grade. In particular, low, medium, and high-grade metamorphic rocks are all fall in the range of 6.0 to 7.0 kilometers per second. The second factor is the depth. Seismic wave velocities increase with depths in the continental crust from 6 to 6.2 kilometers per second at depths of less than 10 kilometers to 6.6 kilometers per second at 25 kilometers per second depth. Lower crustal velocities range from 6.8 to 7.2 kilometers per second, and in some cases show a bimodal distribution. Some continental crust has an evidence of a small discontinuity at mid-crustal depths, known as the Conrad discontinuity, in which wave velocities increase in intervals. The last factor that I'm going to discuss to you is the Poisson's ratio. Because seismic wave velocities are related to rock density, and density is related to rock composition, the measurement of these velocities provides an important limitation on the composition of both the oceanic and continental crust. Poisson's ratio, which is the ratio of P wave to S wave velocity, is a better indicator of crustal composition than either P or S wave data alone. Poisson's ratio rises with density as rock composition shifts from felsic, for example feldspar and quartz, to mafic, for example basalt and gabbro, as well as with temperature. Since S-wave velocity falls faster than P-wave velocity as temperature rises. This shift is linked to systemic changes in quartz and feldspar materials. The ratio rises as feldspar content rises and falls as quartz content decreases. And that's all is my discussion about the factors influencing the wave velocity. Thank you for spending your time with me. Once again, good day and God bless.